So yell at them. I will take a look at it after class as well. All right. Game plan. Remember, exam 3 is this Friday. I'm finishing the material for the exam today. Whatever we cover today is the last bit of material for the test. No office hours on Wednesday. Sorry, I got to go out of town. You will be doing your review for the test in lab. Okay. TA should have something ready for you. Right? And of course, Monday, Veterans Day, is our holiday, so we will not be meeting, but for the rest of the week, we will have lab. So Tuesday, Wednesday, Thursday, whatever day you go to lab, you will still be going there. I've been told that we're not on quiz 10, we're on a different quiz. Okay, so ignore the 10 part. I don't know, they're the ones who said all of this. So you will have a quiz next week in lab. All right. Now, I'm going to say this one more time regarding the attendance because I'm still getting emails about it. I have changed your dog tag in Top Hat. That does not mean that if you've been submitting attendance that it has not been recorded. It is still accepting your attendance. It's just that since I've changed the dog tag, it will now filter into MyLabs Plus. Now pay attention so that way you don't email me about this again. MyLabs Plus and Top Hat are two completely different programs. They do not play nicely together. So I have to manually filter out all of your dog tags, your student IDs from Top Hat, and then enter in your attendance into MyLabs Plus, which is why you have not seen a change in your attendance grade if you did fix it in your information. You will not see a change in your attendance grade until sometime before Thanksgiving break, whenever we pull the data again from Top Hat. Okay? If you are having problems submitting your attendance through Top Hat, you need to contact Top Hat support. I can't fix that. But what I can do, that's why I've had this pink pad of paper up at the front of the room for the last 2 months. Sign it in, and I will manually fix your attendance for you. But you've got to fix your account yourself through Top Hat first. You can't be doing this all the time. Okay? All right. Let's get moving. Okay. So here's the stuff that we've covered so far. On Monday and Friday last week. Any questions? Say what?
No attendance?
Oh, it's coming.
Okay.
I got this.
Make sure.
Okay. Here's what we've done so far with this whole coding theory business. This is the main gist of things right here. Alright? Get ourselves settled here. With coding theory, we started off with this idea of modular arithmetic. Now, key thing, quick trivia, when we're dealing with modular arithmetic, what's the only thing we have? The
remainder.
Okay. We have worked in several cases. Base 2 is the primary base that we're dealing with for all of this stuff. In base 2, the only digits we see are 1s and 0s. Binary, right? Base 2, binary, 2 digits, 1s and 0s. And we started talking about this idea of a code word. It's essentially a string of bits, or a string of 1s and 0s, okay? And we have what's called a generator matrix. The generator matrix takes your message, your little code word, 1s and 0s, and we encode it, we transpose it over to, whatever combination of 1s and 0s we want to work with. When working with a generator matrix, there's 2 parts to it. Okay? It always consists of what we call the identity matrix based on the link to the code word. So if you have a code word, right, a string of 1s and 0s, and you only have 3 digits, what should the size of your identity matrix be? use our examples. We have a code word that is 3 digits long, 3 bits long. The identity matrix that goes with it should be of size 3 by 3 if it's a square. 3 rows, 3 columns. So if you have a code word that is 5 digits long, your identity matrix that goes with it should be size 5 by 5. Okay, make notes to yourselves. This will be very important. How do you know that you have an identity matrix? What are the characteristics? We know it has to be square. What goes along the diagonal?
Ones.
Only ones. Okay? And if you have ones on the diagonal, you have what everywhere else? Zeros everywhere else. Okay, so that's one part of your generator matrix. You have the identity, and then on the right side of your identity matrix, we have the check bits. Now, formulas for how to calculate your check bits we will give to you. Okay, we'll tell you calculate check bit 1 using blah, check bit 2 using mer, so on and so forth. Okay, we will tell you how to calculate your check bits. So once you have your generator matrix, you have to be able to encode one of those code words and those strings of bits using it. Okay? We did several examples on Friday. You construct your generator matrix. Take your identity, calculate the check bits for each row, and then you write your words vertically along the left side of the generator matrix. You only use the rows that correspond to a 1 in the original code word. Cross out any rows that have zeros. We use our modular arithmetic to add top to bottom for those. Okay, now the other thing we did on Friday. Once you know how to encode a code word, you should also be able to determine all possible code words that you can have. That goes back to example 18. Make a note to yourself. For number 3, determining all possible code words of a given length. That corresponds to example 18 on page 58. Page 58, example 18, for this third thing that we've been doing. Now today, we're going to build and use what we call a check matrix. Because remember, once you encode your word using your generator matrix, that word gets transmitted somehow, gets sent somewhere. You send a text message, but then something can go wrong. Right? That new encoded word might get messed up in translation somewhere. So we can use the check matrix to see what exactly went wrong and where it went wrong. So we can actually detect and fix any errors using the check matrix. Remember before, the previous examples we looked at last week, we could detect an error, but we could not necessarily fix it. Today we will actually be fixing the error. Okay? Here we go. First, you have to be able to construct the check matrix itself. So this is stuff that we've already been doing. We have our identity matrix to go along with our code word, and we're going to give a name for that chunk with the check bits. We're going to call that J, matrix J, right? So you have your identity matrix I over here, and then we calculate our check bits, and that's going to make a new chunk of the matrix that we're going to name J. So matrix I and matrix J. Okay. Now, to build the check matrix, all you do is you move some stuff around. Matrix J, remember, consists of all of your check bits. You take that chunk and you put it on top. And then you take your identity matrix and you slide it underneath matrix J, so now you have a vertical matrix. Okay. Now sometimes we have to make some adjustments. So my slide got a little messed up, so I rewrote this for you guys. Example 19. Find a check matrix for these two generator matrices. Okay, here's one way to tell the difference. A generator matrix your identity matrix in part A. It's a 2 by 2 identity matrix, right? The ones and zeros right here. There's I, which means this piece over here to the right of it should be J. Okay? To construct the check matrix, we take J, that's the part that goes on top. Let's rewrite this. So 1, 1, 0, 1. And then you take I and you slide it in underneath, and you get 1, 0, 0, 1. That is the check matrix. Okay? So up here, J, and then underneath it is I. Okay? So for this example, all we're doing is constructing. We're not doing anything with the check matrix yet. We're just showing you how to build it. So in order to get your check matrix, you have to start with the generator. Okay? You have to have the generator generate the matrix first. Now for part B, here's one of those little twists in the example. Sometimes your identity matrix needs to be adjusted to fit matrix J. Sometimes they don't match up in size, so you have to add in a couple ones and zeros. So again, for part B, what's the length of the code word? 2. If you look at the identity matrix, it's in chunks to the far left. In part B, you have an identity matrix that is 2 by 2, and then how many check bits are you adding to your code words? 3. You have a 2 by 2 identity matrix, and then there are 3 more columns that follow it. So those are 3 check bits that are added on. So let's separate this out. There's I, which means this part over here is J. We start by rewriting matrix J first. So 1, 1, 1, 0, 1, 0. Then underneath that, okay, I'm going to put the original identity matrix in here. So 1, 0, 0, 1. And as you can see, we got a couple gaps here. We're missing a couple numbers. So let's add in some ones and zeros to make this a full identity matrix. So we need another 1 down here, and then the rest should all be zeros. So we are forcing an identity matrix under matrix J that matches the proper size of your code words with the check bits. Okay. Nothing fancy, no tricks. I'm just adding in some ones and zeros so it becomes a true identity matrix that fits the proper size. That's it. Questions on generating or creating the check matrix? Yep.
You know where to put the one when you're adding zeros and one.
Okay. We're creating an identity matrix underneath it, right? So you just follow the pattern. You have to have ones along the diagonal if it's an identity matrix, and then fill in zeros everywhere else. So again, notice I didn't add anything to the values for matrix J. I left it alone. That part stayed the same. But for the identity matrix, that's the only thing you mess with. That's the only thing you will add ones and zeros to. Okay. Other questions on creating the check matrix?
Why do you ones first compare down to
That's just because of the check bits. However you calculate the check bits, it is what it is. Okay? Those come from the formula. So in this example, we just gave them to you. We didn't make you calculate them. Last chance. Other questions before I move on? Okay. So that's creating the check matrix. Now, how do we actually use it? In this slide, the matrix on the left, notice you got M1, M2, M3 vertically, right? These correspond to your original message. Okay. Or your code word. This is your identity matrix. And then over here, these are your check bits. That's why it's got the C1, C2, C3. So this is the matrix that we were looking at last week. And the one on the left is all the stuff that we were doing on Monday and Friday. Now the matrix on the right, the vertical one, that is the check matrix. That's what we just looked at in the previous slide. We got to add one more concept here. Across the bottom of your check matrix, you have what we call the syndrome, the output. The syndrome is what tells us if something is wrong and where we did go wrong with the transmission. Okay? So we have the generator matrix that encodes our code word. From the generator matrix, you create the check matrix, which actually check if something went wrong, got lost in translation. All right. Key thing to remember. If a code word was properly encoded and nothing went wrong, code words produce all zeros from the check matrix. If you get all zeros from the check matrix, that means nothing went wrong. Transmission successful. So let's go through this example. We are going to encode the message 101 using that generator matrix. What's the rule if you are encoding? We only look at the rows that have ones. So this row with a 0 in the middle, cross that guy out. And we add modular arithmetic, top to bottom, the remaining rows. So top to bottom, we get a 1, a 0, a 1, a 1, a 1, and a 0. We're in binary. Right? 1 plus 1 is equal to 0. So, we can go over to our check matrix, and we do a similar process. We take our encoded code word, write it along the check matrix. So 1, 0, 1, 1, 1, and another 0. From here, it's the same process. You only take the rows that correspond to a 1. Anything with a 0, keep it crossed out. So let's add this up top to bottom. Okay. A 1 from the top row plus a 1 in the fourth row gives us 0. For the second column, we get another 0. And in the third column, oh look, another 0. Since the check matrix gave us all zeros, that tells us we correctly encoded and transmitted 101.
How did you get the 3 zeros at the bottom?
Same thing that you do with the generator matrix, you add top to bottom. Add your columns top to bottom. So look at the first column, not the one we wrote in. The first column is printed. You got a 1 on top, you crossed out the second row, and then there's another 1 in the fourth row. 1 plus 1 gives you 0. That's where the first 0 comes from. Do the same thing all the way across. Add your columns, top to bottom.
How come you have to transfer the coded one at the bottom of the first one?
That's how the check matrix checks. You are checking, we are checking the encoded word, right? You're checking to make sure, 1, that it got encoded correctly, and 2, that if that's what's transmitted, that's what was supposed to be transmitted. Okay? We're going to do an example where we actually catch something that went wrong. Okay? Other questions? All right. I'm trying to take our time with this. 0 for the first one, that's fine. But in the second column, look, there's only 1 in the second column. So that gives you a 1 at the bottom. In the third column, if you add it up, you get another 1. Now remember, if it's encoded correctly, you should get all zeros. Since we didn't get all zeros, we know something went wrong. Here's the nice thing. Notice, the result that we got, our syndrome of 0, 1, 1, matches the third row. That tells us that something in the third row is what went wrong. Well, look at the digit that corresponds to the third row. It's a 0. That means the 0 is wrong. What's your only other option if the 0 is wrong? It has to be a 1. There you go. That's how the check matrix works. Okay? That's the nice thing about binary. It's a 1 or a 0. You don't have any other options. So if you know it's not supposed to be a 0, it automatically has to be a 1. Question?
So with the syndrome, when you check it, will it always tell you which one was wrong?
Exactly. That's why we like using binary for this.
I have a question.
Yes.
On the light blue, the generator matrix, the only thing we're doing there is deciding which one not to use, right?
Yeah. From the generator matrix, it's the same thing as the check matrix. If there's a 0 in whatever message you're encoding or checking, cross out that row.
Okay.
Always and forever, you only add the columns that correspond to a 1 in the original message. 1's in the original message.
What's the difference between the identity matrix and the check matrix?
Okay, the identity matrix is just a piece of the generator matrix. It makes up the first side of it, and then the check bits. That's the generator matrix. Then you use that becomes part of your check matrix because it goes underneath the check bits. Right? So your identity matrix, okay? Your identity matrix is on this side. You literally take all of this chunk and rewrite it underneath your check bits. That's what we did in example 19.
Check bits are always going to be ID'd as J.
Yeah, that becomes matrix J. Yeah. Okay. Let's see. Examples. All right. Suppose we have that generator matrix. Okay. Let's see. And we need to find the syndrome for a code word 11100. If there is an error, decode if possible. Well, first things first, how long is our original code word? Because notice it's not given to you. The original code word is length 2. And you get that because your identity matrix is 2 by 2. Okay, so this is another way we can write our identity matrix. A little 2 at the bottom says it has to be 2 by 2. Okay, so if it were a 3 by 3 identity matrix, it would be I3. 5 by 5 identity matrix, I5. All right. Well, there's one piece of information that we need. Well, from here, if we're going to determine that that is the correct encoding for the code word, whatever it is, we have to take our generator matrix and create the check matrix. Alright. To create the check matrix, start with part J. So not the identity, all of the check bits. And you rewrite those as 1, 0, 0, 0, 1, 1. Then underneath it, copy over your check your encoded word. So we're going to write in that code word that's highlighted. So copy over 1, 1, 1, 0, 0. All right. We only look at the rows that have a 1 from the original message, or our now encoded original message. Bless you, bless you. So we cross out this row because there's a 0 in the message, and that row because there's a 0 in the message. Okay? So, go to the modular arithmetic. We add our columns top to bottom. Questions?
Yeah, where'd you get to the second one?
Which second
On
one?
the, when you wrote it on the left side of the matrix.
Okay, the zeros and ones, the stuff in black.
Yeah.
Okay.
You cross out the bottom 0, that's where you get the second, 3, 1, you get the second one.
3 ones.
For the second.
Okay, are we talking about the adjusted identity matrix, or are we talking about the original, the word that I wrote on the side?
On the side.
The word that I wrote on the side is that word that's highlighted right there. 1, 1, 1, 0, 0.
Oh, okay.
Oh, read your slides. That's why you got the notes. That's why they're there. Okay, so it says find the syndrome for a code word of 1, 1, 1, 0, 0. Okay, I'm not pulling this out of thin air. So they gave us the generator matrix. We created the check matrix. We take that code word that's highlighted in blue, and we write it along the check matrix. Okay, so we're looking for errors. Add your columns top to bottom, and we get a 0 for the first one. For the second column, well, crap, we got a 1. And in the third column, we have another 1. Well, this corresponds directly to the second row, which means our digit in the message should not be a 1, it should be a 0. Okay. So that means that should be a 0. The correct message should have been encoded as 1, 0, 1, 0, 0. So the main thing about example 20, I did not ever give you the original code word. You can actually find the errors in the encoded word without the original. Okay. Questions?
Yeah, so does that mean that like none of the I can like never be able to say because like I was saying when we last up you wouldn't know which one it corresponds.
They will always be the same. So
I can like 2 rows be the same though.
say it louder.
2 rows be exactly the same
That depends on the checked bits, but since we're working with an identity matrix, the identity part, the bottom part, will never be exactly the same because of the ones on the diagram. Identity matrices are unique. If it does happen, I'm not going to give you questions like that on the test.
Okay.
Other questions? Yeah.
Is there a way if we calculated our matrix wrong, we would miss that?
That's where you have to be really careful.
What do you ask?
Okay, is there a way to determine if you set up your matrix wrong? That one, no. The only thing that we're catching is the error in the message itself and the encoding of the message. Yeah. So watch your math whenever you're actually creating your generator matrix. Thank you for saying something with the checked bits. Okay. Other questions? Go louder.
We have this, like we say on the exam, there be identity matrices with only 2 by 2, or will it be more?
I'm not sure what you're asking.
Okay, like each example that we've done is been like 2 by 2. For the identity matrix.
Yeah, for this example, it's a 2 by 2 identity matrix, right?
Would it always be like that?
Nope. I could give you a giant matrix that has a 3 by 3 identity matrix to it. You have to be able to visually identify what the identity matrix looks like, and that will tell you how long your code word is. tomorrow